Hello dear students, in the last class we talked about displacement time, position time and distance time graph and their interconvergence. So today I'll be talking about velocity time graph. It's the most important graph, kinematical graph, because it tells about all the information of motion. From the slope we can come to know about the acceleration, from the area we come to know about the displacement, distance, and its velocity is already there because it's velocity time graph. So this is the graph that contains all the information directly. So let's see various points about the velocity time graphs. The first important thing is the slope of velocity time graph. The slope of velocity time graph is the acceleration dv by dt. So from the slope we can get to know about what is the acceleration, whether it is uniform, whether it is increasing or decreasing. So I can write that the slope. And you know one thing that if the graph is a straight line, it has a uniform slope everywhere. Slope is acceleration. If acceleration is uniform, means slope is uniform everywhere, means the graph is a straight line. So what we can say that the motion, the Vt graph for the uniformly accelerated motion would be a straight line. And now suppose particle is moving along this x direction, positive x direction, and we have chosen this to be positive direction, and let me draw few velocity time graph in which the acceleration is uniform. So suppose velocity time graph is like this straight line. Its slope is 0, mean the acceleration is 0, but it is moving along the positive direction. So if this is the x-axis along which it is moving, so it is moving along the positive direction like this. And if the velocity time graph is like this, this is also a straight line parallel to t-axis, slope is 0, acceleration is 0, mean velocity is constant. Here the velocity was constant in the positive direction. Now the velocity, this is the positive direction of motion, and velocity is the particle is moving opposite to the positive direction like this with a constant velocity. So this velocity is always negative. And then we can have velocity time graph like this, like this, like this. In all these three cases, acceleration is positive and constant because the slope is positive. Initial velocity here is 0. Initial velocity here is positive, initial velocity here is negative. So these motions can be represented by this is the positive direction. It start from rest and moved along this direction. And what about this? This motion start from some positive initial velocity and a positive acceleration. So it start with some positive initial velocity and the acceleration is also along the same direction. And in this case the initial velocity is negative, but the acceleration is uniform everywhere positive. So this motion represents, this is the positive direction and the particle starts this direction and the acceleration is in this direction. And you can see that whenever this kind of motion will be there will be turning, because there will come a moment when the velocity will be momentarily come to a stop, and then it will go in the direction of acceleration, and that is the moment where turning occurs here. So at this moment, just before this moment, velocity was negative, after that velocity is positive. And then we can have this type of Vt graph also. Here also the graph is straight line, but at all these three group, acceleration is negative, negative acceleration. It started with 0 initial velocity, it started with positive initial velocity, and let me draw this like this, and it started with the negative initial velocity. So here the motion would be, this is the positive direction and started from rest, and along this direction it has a uniform acceleration. In this case, it started with some positive initial velocity like this, and acceleration is throughout negative like this. So again here velocity and uniform acceleration are opposite, so there will be turning. It will come to a momentary rest, then acceleration will bend the particle in its direction. That turning is here, and here this is the positive direction, started with negative initial velocity, and acceleration is always in the direction, so there will not be any turning. So we have taken few cases of uniform acceleration. In a uniform acceleration, the graph will be one single unique straight line. If the acceleration changes and still it is uniform, that will be a new straight line. So long as particle is moving with one unique acceleration, the graph will be a unique straight line. And now let's see some other types of velocity time graph. So suppose the velocity time graph is something like this. So in all these cases, we can see that the graph is cutting the time axis. Cutting mean it is crossing time axis from one side to other. It can go like this, it can go like that, and the graph could be anything, need not be a straight line. So this is the point where the graph cuts, and obviously the point where the graph cuts, velocity is 0, and just before that point the velocity is positive, here negative, here velocity positive, negative, here just before velocity negative, then positive, here the negative and positive. So positive to negative velocity or negative to positive velocity change, that means the direction has changed. So we can say that direction has changed at the moment of crossing velocity 0. So what we can say, that whenever velocity time graph cuts time axis, that would mean that the particle has turned. It can turn from going to positive direction then coming back to negative direction, or it can be going towards negative direction then coming to positive direction. In all these cases, the velocity time graph will cut the time axis. So other important thing I can state that so if velocity time graph cuts time axis, that would mean that turning has occurred. And we also studied that area bounded by velocity time graph gives the displacement. Here it's important to recall that the area bounded by curve can be positive or negative. If the area is above time axis, that area is positive, and if it is below time axis, that is negative. So suppose this area, and you can see that there is a turning here, and the turning occurs at say time t0, and the overall time of motion is t, and this area is a1 and this area is a2, and these area are to be written with sign. The area above t-axis would be positive, below t-axis would be negative. So overall displacement for the whole motion till time t is summation of all area, and obviously these area to be written with sign. And we can tell about the distance traveled also. If there is no turning, then distance traveled is equal to the magnitude of displacement. If they are turning, then we have to calculate distance in an interval in which the body has not turned, and the summation of all such distance is the total distance. If we look, this motion started from rest, its slope is positive, mean with positive acceleration, and then it come to rest here, then it turn, and then again finally come to rest. So this motion is something like this. Suppose this is the x-axis along which the body moves. So it starts from here, it moves like this, comes to rest at t is equal to t0, then returns. So if we see the overall distance, so distance is the sum of distance in this part and this part. area here, this area is A1. So this area A1, the magnitude A1 is distance, and this area is A2, and the mod A2 will be distance from here to here. So if we want to calculate the overall distances, so what we need to do, distance can't be negative. We need to do just one thing, mod A1 plus mod A2. And we can also talk about one more thing. Whenever nothing is written, this is v. So what we will understand that this is a velocity, but the symbol for a speed is also v. And we want to convert a speed time graph from velocity time graph. So let me write the speed with black color. So it's very simple thing. Speed is magnitude of velocity. Speed can't be negative. So if the velocity is positive, so we can say that speed is equal to v. And if velocity is negative, so negative of that velocity will be positive, that will be speed. So I can write that speed is equal to, okay, this is not correct, the speed is the mod v, and for the velocity, okay, I'll write the whole thing. So speed is equal to velocity if velocity is positive, and is equal to minus of velocity if velocity is negative. So that will make speed positive, as it is always positive. So if I want to make the velocity time graph, if I want to convert velocity time graph to speed time graph, what I should do? If the graph is on the positive side, if the graph is positive, so speed would be the same as velocity. I will not change the graph, and whatever part is below time axis, there the velocity is negative, so I will have to convert it to positive. So what I will do, I will make the mirror image of the graph with respect to time axis. So from here to here velocity is positive, so speed is same as velocity. So the speed time graph would be like this, and this part is negative, so speed would be the negative of that, so speed time graph would be like this. So this way we can convert velocity time graph to speed time graph. So let's see a very important case of motion in which particles start from rest, moves uniformly for a time t1, then moves for uniform motion with constant velocity for time t0, then retards uniformly for time t2 to come to rest finally. And we have to plot the velocity time graph for this whole motion, and it's very important case, and usually it happens when we start from rest to rest. And the only good thing I am taking that the acceleration and the retardation are uniform. So actually this is also acceleration, but this is zero acceleration. A unique acceleration will have a unique straight line. So this graph will comprise of three unique straight line, because we have a three unique acceleration. This acceleration is actually minus a2, this acceleration is 0, this acceleration is a1. It start from rest, so this graph would be positive acceleration. So this graph would be something like this. It reaches to a peak velocity at this point, and we can get this peak velocity here by the first equation of motion, v is equal to u plus at. So this peak velocity will be u is 0, acceleration is a1, time is t1. So here it will reach to peak velocity, v max is equal to a1 t1. So it has reached up to here. This velocity is a1 t1, and this time interval for the uniform motion is t1, and the slope is a1, so obviously this divided by this the slope, and that is a1 t1 by t1 is a1. And now it moves for time t0 for uniform motion. So from here to here it has a velocity same as a v max. So up to here the velocity is v max, and that is a a1 t1. So for here to here, the graph is a straight line parallel to t axis, acceleration is 0. This time interval is t0. and finally it will come to rest in time t2, and we know that the acceleration is uniform, so graph has to be a straight line. So this is a straight line, and its slope is minus a2, because the acceleration is minus a2, and if the slope is minus a2 mean the a2 is a1 t1 by t2. So a1 t1 by t2 is a2. So actually this velocity can also be written as a2 t2. From here, if you want to apply the first equation, this is the initial velocity, this is the final velocity, so you can write final velocity is 0, initial velocity is a1 t1, acceleration is minus a2, time interval is t2. So one good thing that we got that a1 t1 is equal to a2 t2. So this peak velocity is a2 t2, and that is also a1 t1. And one more good thing, that if the a1 is equal to a2, so that would mean t1 is equal to t2, mean if body accelerate and then retards at the same rate as the acceleration, then time during phase of acceleration and time during phase of retardation would be same. So these are few things that, and then if we want to calculate the overall displacement, then from this area we can find the this area will give the displacement for the whole motion, and then if we divide that displacement by the time interval, we will get the average velocity.